Welcome back to another training session for OpenDSS-G. In this opportunity, we're going to talk about harmonic simulation. And for that, I've selected one of the harmonic examples provided with OpenDSS-G, which corresponds to the equivalent of an example in the IEEE 519 standard, in case you want to check for it. So for that, I'm just going to highlight the buses and the bus names. Initially, I'm going to describe how the system works and what are the components related into it. So first, we have the substation. We have a transformer, step-down transformer. And then we have another step-down transformer from medium voltage to low voltage for 3 different loads. So here I'm going to locate the substation or service transformer, which is located at the source bus. We have 3 loads. 2 of those loads are inverter based and are adding harmonic distortion in current. And one of those loads, the third load, is just a linear load, which could be just a resistive load. We also have 2 switches for connecting and disconnecting the loads that we have connected through inverters. And one of those loads also incorporates a storage and a capacitor. Of course, those are not part of the IEEE 519, but were added just in case you want to play a little bit more with those. Here are the different transformers that I was talking about before. And finally, we have the switches. So we can see those switches for connecting or disconnecting the loads that are introducing harmonic distortion and current. Now we have different transformers for each one of the loads connecting, and they have different configurations just for doing the trick that we're trying to do here. So the first step we're going to do is just make a very quick snapshot for initializing the system. Now let's talk about a little bit about the monitors that we already have installed in this example. We have one monitor installed upstream, very close to the substation, to measure the total harmonic distortion at the point of common coupling. The idea is to see what's the effect when adding the different loads into the system when they get connected and their contribution in terms of harmonic distortion. Also talking about the transformers that we have in the system, the ones that are connected at the point of common coupling to the loads, we can see using the explorer that those transformers have different configurations. So just by using the explorer, you can go ahead and look that the configurations could be delta, 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 Y. This for shifting the phase angle of the current for each one of the loads, which is basically the effect that the IEEE 519 is proposing in this example. To see right now, I want to show you also the contribution in terms of harmonic distortion for each one of the loads. So for that, I'm going to create a monitor on each one of the loads. For that, I'll go ahead and at the meter management, and I'm going to create another monitor. I'm going to call it my mon, just to give it a name. I'm going to do it for loads, and I'm going to apply it to all the loads in the system. And I'm going to create that. With this tool incorporated in OpenDSS-G 4.5.03, we can create monitors at each one of the for all the elements within the same class in OpenDSS, which is very convenient many times. Here we can see that we have created monitors for all the different loads that we had in the model. And those are going to have the same type and are going to follow the same type of measurement for each one of those. Also, I want to show you the spectrum that each one of the elements of the loads have. So we have 2 different types of spectrum. We have the linear and we have the inverter type. The inverter type, in this case, called spectrum_2, and we can see the different harmonics that are in place. We can see the current waveform that we are generating and the different, numerical values for each one. We also have the linear load, which, well, is very simple. It basically only has contribution at the fundamental of the harmonic spectrum. So we have two of the loads who are adding harmonic distortion, which means they have spectrum underscore 2, and the linear one, well, we'll have just spectrum underscore 1. Let's go back into the simulation, and let's configure the simulation as a Harmonics T simulation. This because Harmonics T solves several problems that, well, can be seen with Harmonics, so Harmonics T is always a good option. And also will allow us to reconfigure the system by opening and closing switches. I'm going to show all the monitors just to show you live what's going on. So all the monitors right now are in harmonic mode. If I change the simulation mode, they're going to change their aspect. But since the last simulation mode was Harmonics T, they're gonna be in Harmonics mode. So right now what we're seeing are the total harmonic distortion in voltage at the point of common coupling, and the same for the different loads. So we can see there are loads that are injecting harmonics, but some others, some others don't, and the result at the point of common coupling is that we have no harmonic distortion, which is very interesting. We can see this in terms of the harmonic spectrum. We can see that the total contribution after this addition, the point-to-point summation of all the harmonic contributions give us 0 at the point of common coupling. We can see also the current waveforms here. We can see the one at the point of common coupling, which looks very good, and we can see the current waveforms for all the different loads. So the linear looks pretty good, and the other ones injecting harmonic distortion, well, are distorted as expected. We can do this just by checking voltage, current. We can do the same, just synchronize all the monitors to show the same information. We can see that the voltage waveforms are pretty bad in the case of the inverters, but otherwise pretty good at the point of common coupling and the linear load. Now let's try to play a little bit by changing the state of the switches. For that, I'm going to bring a switch panel. I'm going to select the area that comprehends both switches, the ones I have in my model. We can see the location, and just by double click on them, we're going to disconnect some of the load. So the first step will be to disconnect the linear load. I'm going to disconnect it. We can see in the diagram that the switch is open, which is in green, and we can see that the amount of harmonic distortion that we have at the point of common coupling increased a little bit, but still pretty good, since the inverter loads are, well, basically operating properly, and, well, they're just canceling the harmonics that they have. Now let's disconnect one of those, and let's see what happens to the current at the point of common coupling. When we leave just one of the inverters, we can see that at the point of common coupling, the total harmonic distortion in current is basically the equivalent of the one that is injected by the inverter load, the only one that is connected to the system. So we can navigate and see how bad it is. And well, basically this confirms the hypothesis proposed by the IEEE 519. So now let's add the linear load to see how by increasing a non-contaminating, well, by increasing the demand with a non-contaminating load will help reducing the amount of harmonic distortion. Yeah, the curve, the waveform looks a little bit better. Actually, we can go and see the spectrum. Yeah, it's not as bad as it was initially, but still we can do better. So let's connect the other load to the delta-delta transformer, and we have eliminated completely the harmonic distortion and current. So you can keep playing with this example and use it for bring together other examples using larger models. So it's up to you. So this was just a fast example to show you how the harmonic distortion simulation works. Enjoy.